Assalamualaikum and a very good day to Dr. Nazri. I am Nurul Syahira binti Ahmad Azrul. Today, my team members and I from Group 17 would like to present our project titled Biometric Distribution System for Food Aid. To begin with our introduction, the main issue we are tackling is the inefficient manual tracking fields to guarantee fair food allocation. Because of this problem, there is an urgent need for a biometric distribution system for food aid in order to support SDG 1, which is no poverty. To achieve this, our goals are threefold. Firstly, we want to replace vulnerable manual paper ledgers with automated RFID smart card tracking. Secondly, we enable non-blocking operation by using asynchronous software timers so the systems run smoothly. And thirdly, we want to establish secure audit trails by integrating Blink IoT for real-time remote monitoring. Looking at the key features, the system relies on RFID biometrics controlled by a structured finite state machine, and we utilize Blink IoT to automate fair food allocation for SDG1. Ultimately, the main benefit of implementing this project is to guarantee a tamper-proof audit trail and strict data integrity, which is crucial to secure fair food allocation for SDG1, which is no poverty. Moving on to our project objectives, first we aim to implement secure RFID tracking by designing an ESP32-based distribution station that use RFID smart tokens for reliable refugee verification. Second, we want to develop a non-blocking finite state machine control logic using asynchronous timers to manage role separation and prevent any system freezing during real-time operations. Finally, our third objective is to integrate the Blink IoT platform to establish an interrupt-driven data pipeline for live remote configurations and secure transaction logs.
I am Lim Min Fong. Now I'll be focusing on the data processing part. Our data processing workflow is driven by 6 key technical components. Firstly, the ESP32 acts as our central processing unit. It is responsible for receiving inputs from the RFID reader and the matrix keypad, while concurrently managing a stable Wi-Fi connection to the Blink IoT platform. Next, we leverage the ESP32's efficient 32-bit reduced instruction set computer RISC architecture. This 32-bit structure detects exactly how much data is processed per cycle, allowing us to easily manage arrays of user IDs and food quotas. The RISC design minimizes the required CPU cycles and ensuring rapid logic execution. Besides that, our software flow is also controlled by the finite state machine, or FSM. The system begins in a default idle state while waiting for an IFT cascade. The SSM guarantees smooth and logical transition between detecting user, displaying their food limits, and securely accessing the administrative mode. Furthermore, we implemented non-blocking timer optimization. To avoid the system freezing during traditional working delay, we utilize the asynchronous software timers for visual identity feedback, ensuring the terminal remains responsive. After that, the ESP32 Extensa LSS dual-core architecture enables true concurrency. We optimize the data processing by isolating local real-time tasks such as keypad polling and LCD updates onto one core, while the second core handles the background tasks. Lastly, the system supports real-time data monitoring. Whenever the admin mode is utilized, the processor automatically forwards the newly updated limits to the Blink IoT cloud, which enables real-time administrative monitoring of the entire distribution process.
Now let's look at the data storage architecture of our system. As shown in the pyramid diagram, our data storage layout is strictly structured across a 5-level memory hierarchy from high-speed registers to the remote Blink cloud. This design is highly critical to optimize data access times and maintain overall structural efficiency during the biometric distribution process. For the first level, which is high-speed register architecture, we are utilizing the dual-core Extensa processor 32-bit registers. What this does in reality is that it drastically accelerates our function calls. This hardware execution layer allows the system to instantly process immediate physical actions, like capturing the 4-byte RFID card data and executing fast FSM state transition on the spot. Next, to bridge the speed gap between the fast processor and the slower external memory, we have stage 2, which is the flash cache layer. This MMU-based hardware cache maps external flash directly to the on-chip memory. By doing this, the CPU can fetch frequently executed instructions from fast SRAM, which significantly accelerates our repetitive code loops and FSM pooling routines without putting unnecessary load on the SPI bus. Moving on to stage 3, we look at the internal SRAM, which acts as the core operational hub of our system. We deliberately separate dynamic runtime variables from the flash cache to eliminate any lookup delays. This high-speed internal SRAM is where dynamic parameters like FSM states and non-blocking timer counts reside directly during runtime. Furthermore, this SRAM zone is responsible for running the entire system firmware, actively managing background-free RTOS Wi-Fi logic, and processing real-time add quota deductions before the final data is synchronized to the cloud. Looking at level 4, first we use immutable external flash storage. The external SPI flash houses only the compiled static firmware and immutable data like Wi-Fi credentials and baseline user profiles. We deliberately avoid writing dynamic transaction data here to avoid write latency and memory wear. However, because we don't write active transaction update to this local flash, a sudden power failure will completely erase any temporary data stored in the volatile SRAM. To solve this problem, we focus at the last level, which is cloud reliance for data persistence. True data persistence relies entirely on the remote Blink IoT platform, which secures real-time transaction logs and user balances over a Wi-Fi link. By offloading this storage to the cloud, our digital ledger remains fully safe and completely immune to protect against local power loss, allowing for a highly secure and transparent resource management system. Lastly, to evaluate the efficiency of our data storage layout, we conducted a mathematical performance analysis using a multi-level memory performance equation. We assume the values that we want to substitute into this formula. For example, as shown in the center container, the hardware access times are derived from standard ESP32 specifications and network latencies, spanning from 1 virtual clock tick for internal registers up to 500 ticks for Blink Cloud access. So, by substituting all these latency values and optimized hit ratios into the formula, the calculation proves that the average system access time is only 1.41625 virtual clock ticks. This mathematically demonstrates that caching transaction logs and profile locally inside the internal RAM successfully eliminates critical cloud transmission delays, keeping the edge terminal operating at near ideal speed.
So this slide explains the data movement of our system. The data first enters the system from three main sources. The RFID card is scanned by the MFRC522 reader, and the UID is transferred to the ESP32 through SPI. The 4+4 keypad sends users input to ESP32 through GPIO metric scanning. Besides that, administrator updates can also be received from Blink Cloud through Wi-Fi. So after receiving the data, the ESP32 acts as a central processing unit. It checks the UID, processes the enter amount, and compare it with the available quarter, and use the FSM to control the correct data flow between different states. Temporary runtime data is stored in SRAM during the process. Finally, the processed data is delivered to output devices. The LCD displays the results through I2C. The LED shows the system state through GPIO, and the ESP32 update quarter information, trans-scanning records, and log to Blink Cloud through Wi-Fi. This allows both local feedback and real-time remote monitoring.
Let's look at the control and management firmware. This system architecture is built on a 6-key pillar that ensure reliability and security. First is our finite state machine, which control the entire system operation. It ensures orderly execution of tasks and prevent invalid transition, which significantly improves system reliability. For the second, authentication control relies on RFID card verification. Here, whether user can access system function while invalid cards are rejected. If an unauthorized card scan, a red LED and LCD will display error message instantly. Third, for the input monitoring, we utilize an MFRC522 RFID reader and a 4x4 metric keypad. The system manages this input using program I/O polling to continuously check for the user interaction. Fourth, we implement a hybrid I/O machine. We use polling for RFID and keypad monitoring for instant response, but switch to interrupt driver I/O for background tasks. This setup efficiently support multitasking. Then for the quarter validation, the firmware check the enter amount against a variable quarter to prevent existing allocation limit. This process automatically protects food resource from misuse. Finally, our security feature ensure complete unauthorized access prevention. We have transaction blocking for invalid requests to head back input with everything securely managed under control state transition. So the next slide is detail on how our system handle user internal memory and data tracking. First is user profile management. This module store register user information, keep track of RFID identification record, and manage individual food allocation record. Second, the resource management actively track the remaining food quarter. It updates the quarter after each successful transaction to ensure accuracy and strictly prevent over allocation of resource. Third, for memory management, user data is stored in the ESP32 SRAM. These local caches allow fast access to user record, keeping the overall system operation efficient. Fourth, the runtime variable management handles temporary data during operation. Key examples include keeping track of the selected user, selected category, enter amount, and the system current state. The administrative management to secure local setting, only administrator RFID card can access admin mode. This enforces the role-based access control to restrict the unauthorized change. Then we integrate Blink cloud-based management. This allows administrator to manage user record remotely, enabling them to modify quarter, reset allocation, and clear the transaction log from anywhere. Finally, the data security tie these components together. It ensures restrict access to sensitive function, guarantee a protected system configuration, and maintain overall control resource allocation.
Hi, my name is Limayi. I will explain the operating support system used in our biometric distribution system for food aid. The first component is RTOS, which enable multitasking on ESP32. It allowed the system to handle RFID scanning, keypad input, LCD updates, and Wi-Fi communication simultaneously, improving overall responsiveness. The second component is Wi-Fi communication, which connect the ESP32 to the internet and enable real-time synchronization with the Blink Cloud platform. Blink also provides the cloud-based monitoring and management. It displays user information and remaining food quotas while allowing an administrator to monitor the transaction remotely. In addition, several software libraries, including RFID, LCD I2C, Wi-Fi, and Blink library, support the integration of hardware and communication function. Finally, the walkway simulation platform was used to model, test, and validate the system before physical implementation to reducing development costs and debugging time. Based on the simulation result, the system successfully achieved its intended functionality. RFID authentication successfully verified registered users, food quota allocation, and redemption operated correctly, and real-time monitoring was achieved through the Link IoT platform. From the FAOS perspective, the system design was effective, the function of secure authentication and quota management was successfully implemented, the architecture integrated the ESP32 with the RFID reader, keypad, LCD display, LEDs, and cloud services. The organization enabled efficient communication between the hardware and software components, while the FSM-based structure ensures systematic and reliable operation. However, the system still has some limitations. It depends on Wi-Fi connectivity, user quota data is not permanently stored, and the project has been validated through simulation only. For the future improvement, including adding in-prompt or database storage, implementing fingerprint authentication, and developing a physical prototype with the automated food dispensing. In conclusion, the biometric distribution system for food aid was successfully designed and simulated using EEE379, RFID technology, pre-RTOS, and the Blink IoT platform. The system achieves secure user authentication, food quota management, real-time monitoring, and efficient multitasking performance. It also improved accountability and efficiency in food aid distribution while reducing manual tracking processes. Overall, the project demonstrates the successful integration of embedded system and IoT technologies, providing a practical and cost-effective solution with strong potential for future real-world deployment. Thank you.